Welcome everybody. This is our second discussion on friction and how it deals with, how we can deal with it mathematically. We did come up with the friction formula last time we spoke, and we said it was less than or equal to the coefficient times the normal. We had enough discussion on that where you should understand now why it's less than or equal to. And it always opposes motion or potential motion. So the whole potential motion thing we didn't hit on very well, but if we had a ramp, there's a potential motion in this direction caused by the part of the force of gravity that is down the ramp. And if the thing is not moving, then the reason it isn't moving, if there aren't any other forces, would be friction, which would be completely opposite of that. Okay, so that's what I mean by potential motion. Like if friction wasn't there, it wouldn't be moving. Or, another way we could talk about that is if I'm pulling on a box with 10 newtons and I can't get it to move, and there's nobody on the other side, then it must be friction that's pulling on it 10 newtons in the opposite direction. So there doesn't have to be movement in order for there to be friction. And even if there is movement, there doesn't have to be acceleration in order for it to be friction. So let's just look at that now. We talked about that for a second. If I have a box that has a velocity that's non-zero in that direction, and there's no other forces that we can see, but there's an acceleration in this direction, how could you write up your summation of forces? Okay, well, we know that there's the force of gravity, right? But when we do our summation of forces, we're talking about the parallel forces, or the ones that are in the same line. So the part of gravity that's down the ramp here would be, sine theta mg, okay? So our summation of forces would be the force down the ramp, keeping in mind that's not a real force, it's part of gravity. And then if there's an acceleration up the ramp, then, well, first of all, how would I draw my vector for that? Same, smaller, bigger? Bigger, right? Because if there's an acceleration in this direction, then there has to be a summation of forces also in that direction to cause that mass to accelerate. So my summation of forces would be force down the ramp plus, in this case, kinetic friction. So that's what this would be. This force would be kinetic friction. So the summation of forces then would be equal to, sine theta mg minus the coefficient times the normal. And minus, then, the way we have this written, indicates a direction, right? So let me just ask you, if you understand vectors, what direction is minus in? The opposite of positive, but in this case, it would be in this direction. So upward would be called a negative, according to this summation of forces. Okay, so if I have a non-zero velocity, I can have a frictional force that's bigger than any other force. But, like we talked about before, yesterday, our frictional force formula is written less than or equal to the coefficient times the normal, because there could be a small incline and my force of friction doesn't have to be maxed out as coefficient times the normal. It just has to be equal to and opposite of the force of gravity that's down the ramp. Okay, so that kind of brings us into today's discussion a little bit more. So we can say from now on that friction is fun, right? Because without friction, how much fun would we have? I mean, think about it. Isn't friction very fun? Yeah, so we call it the fun formula because it looks like fun and it is fun. I mean, this might look like fun here, but the funny thing is, it wouldn't be fun because without the fun, you can't run. Can you? Because you don't have any friction. This probably doesn't look like so much fun, but in reality, there's no way we could do anything really that we can think of without friction. I mean, you might think, though, if you're in space, you can throw something one way, you'll go the other way according to Newton's laws, right? But the only thing is, in order to throw something, you need to use your muscle attachments, and I'm pretty sure the muscles are attached through a friction fit too. So anyway, now that we know that friction is fun, okay, so we go down a little further in the packet, we can see this coefficient of static friction, coefficient of kinetic friction. Now, what does the coefficient mean? Well, I'll explain it here to you. Let's say that I have a surface that is like this, and I'm rubbing it against a surface that is like this. There's going to be some friction there, right? But what if I have a surface that's like this, and I'm rubbing that against a surface like this? Would you imagine that these two surface interactions would be different? Yes, thank you very much. So this one would have a large coefficient. This one would have a relatively smaller coefficient. So the coefficient is a relationship between the two surfaces that we're studying. Okay, so that's what a coefficient is. Or maybe that would be a good lab idea for somebody someday. We have some kind of common coefficients right here that we can use for our problems. But even these aren't perfect. I mean, if you're going to do the lab, part that's going to have some friction in it, part of the lab is going to have to be, I need to determine what the actual coefficient or the relationship is between these two particles. So like if you would do a lab, you would have to do other labs just to make sure that your lab that you actually do are valid. That'll happen when you get further on in your science studies. Okay, so if we look at some formulas, we read some problems. I'm just going to take this out here, and we're going to look at some things. So first of all, let's say that we have a box here, 10 kilograms, and we have a pole here of 10 newtons, and we have a coefficient that's equal to 0.11. And the question is, what's the acceleration? Okay? Okay. It's kind of like that opener problem that we had, I think, on Friday. So the summation of forces in this case is the force of tension to that rope. And you can put plus the force of friction. So the summation of forces in this case is 10 minus the coefficient times the normal. Summation of forces is 10 minus 0.11. And the normal in this case is going to be equal to the weight, right? So that's the weight of 10 or 100 newtons. And this here then would be the normal, 100 newtons. Okay? Okay, so the summation of forces in this case then is negative 1 newtons. Okay, so if you look at this, the question is, what's our initial V? If our initial V is equal to a non-zero number, this is the true summation of forces, and the thing will be slowing down or accelerating in the opposite direction. Let me just fix that here. It doesn't change the way we're talking about it, but the actual number is negative 1, not negative 0.1. But like I said, if it's non-zero, it's going to be accelerating in this direction, right? And to figure out the acceleration, then it's the summation of forces divided by mass equals acceleration. So it's 1 divided by 10 equals 0.1 meters per second squared in the opposite direction of the tension. Any questions about that? So let's see what happens if we change this into 100 newtons. So now we have a tension of 100 newtons, or a pull on that rope at 100 newtons. So now our summation of force is 100 minus coefficient times the friction, or the normal. So it's 100 minus 0.11 times 100, and our summation of forces in that case equals 89 newtons to the right. Got to get that direction in there, okay? So the acceleration then is going to be the summation of forces divided by mass, 89 divided by 10, 8.9 meters per second squared in this direction. Okay? Okay, so let's try this once. Let's say that we have 100 newtons here. Let's say that we have a tug in 30 degrees of 100 newtons. Let's say that our coefficient is 0.333. The question is, what's the acceleration? So the acceleration, you should know already now, is the summation of forces divided by the mass. We'll just say that v sub naught is equal to 0 here. So our summation of forces, then, well, first thing we have to do is find out if this thing is going to be picked up off the ground. Well, we know that that's going to be the sine of 30, that's 50 newtons, right? I don't have to do that SOHCAHTOA stuff anymore, you know that? And then the force that will be directed along the surface will be then 86.6 newtons. So that then is the number that's going to be fighting friction, right? So the summation of forces in this case is going to be, and I'll just write it here, 86.6 newtons minus the coefficient times the normal, all divided by 10 kilograms. Okay, so let me move on. 86.6 minus 0.333 times, the normal in this case is not equal to the weight. Why? Because there's a pull-up that is working with, because normal, the force of normal is equal to the amount of force that the surface has to apply to the object so that the object does not fall through the surface. So if this rope is helping out, well, that's going to be that much less than the force of normal. So in this case, the force of normal is going to be 50 newtons. Okay? So it's going to be 50. And that'll all be divided by 10. And so we get an acceleration of the system equal to 6.995, thank you very much, Sage, meters per second squared in that direction. And that is our acceleration. Any questions about that? Okay, let's just look at this here, not completely, because we don't have the time, but let's just say that I couldn't get to that box, so I had to use a stick to move it along the surface instead of pull it, which happens. The older you get, the more intuitive you are about moving things without injury. And in this case, then, is the normal going to be equal to 100 more or less than? More, because now I'm going to have a force that is pushing into the box, and so therefore the force of normal is going to have to be equal to that much more. Whatever this is would be that much more than 100 newtons, because now the surface has to keep the box's weight up plus whatever else is pushing on that. So now that we have a partial understanding on friction, I want to take a look at this problem here. Okay, so we have a ramp, and of course the massless and frictionless pulley. We have 20 Newton mass or weight. We have another 10 Newton mass, and we have another 10 Newton mass, and we have, we'll just say 30 again, and we'll say that our coefficient of friction here is 0.222. My question is then, what is the acceleration of the system and what are the two tensions? Okay, I changed the picture just a little bit here. And changed again once more. Okay, so first thing is we have to figure out which way this thing is going to accelerate, if it accelerates. We don't know for sure if it's going to accelerate when there's friction. You never know. But if it accelerates, it looks like it'd be 10, right? Because we have 2 sines of 30, which this will be 5 newtons. This will be 5 newtons. Keeping in mind we're getting that out of our force of gravity, right? So that's 5 newtons, and then we got 20 newtons over here. So if this thing accelerates, it's definitely going to go in that direction. Do you agree with that? Okay, so now the next question we have to ask ourselves is friction enough to make up for that other 10 newtons? Right? So keep in mind that the force normal is going to be coming out this, oh, that wasn't quite perpendicular, but it's coming out, pushing on the box from the surface of the ramp, and it's equal to but opposite of this part of gravity, which this then becomes cosine 30 times 10, which is 8.66 newtons. So we can just go ahead and say that we have another force normal here that's equal to 8.66 newtons. Keeping in mind it's fighting off this part of gravity, and that's why it's cosine theta Fg. Okay, so now we still don't have our friction though, right? Because that looks like a big number. Those alone would overcome 20 newtons with the other 10, but we only take into account, you know, a portion of the normal, because the whole friction formula, remember, is friction is, well, less than or equal to the coefficient times the normal. In this case is 0.222 times 8.66, which friction then on each block ends up being 1.9226. Okay, so now we know without a doubt, since the 2 frictions plus the 2 5 newtons downwards, they are not going to equal 20. So we know that this thing is going to accelerate. So I'm going to put in then my friction number right here so I don't forget. Okay, so we have 1.923. And really that should be a much smaller arrow, right? Because we're talking vectors here. Size matters. So if I'm saying that this length of arrow is equal to 5 newtons, then, you know, this length of arrow is going to be equal to, or closer at least, 1.923 newtons. And that's the force of friction. That'll be on both of these, right? Okay, so friction here is 1.923 newtons. Okay, now that we have all of our forces kind of in line, we can write up our summation equation. Okay, so, you know, we can do it with tensions first, we can do it with accelerations first. I guess I kind of like to do it with tensions myself. So I know that T1 that I label here and T2 are the same thing, because you can't push nothing according to Newton's third law. So we're just going to start there, and we're going to say T1 is equal to T2, and we can define T2 right away easily by 20 newtons, and it's going to be plus or minus 2AS. Minus 2AS, I guess I already put it up there, because it's falling with the mass, right? So T1 then, I can say, well, it's going to be, I'm going to start way over here, 5 newtons, that's this, right, the part of gravity down the ramp, plus friction, which is, well, maybe, yeah, plus friction right here is 1.923. Go to the next mass, plus 5 newtons again, plus friction again, 1.9, oops, plus 1.923. Kind of went off the map there a little bit. T1 equals T2. Okay, and then is acceleration of the system going to be a plus or a minus in this case? It's going to be a plus, right? Because it's going to be moving this up, so it has to have more force than all that stuff. So it's going to cause more tension. So it's going to be plus than 2AS, right? Because it's really just 2 kilograms on each end. Okay, so now you put all this stuff together here. Okay, so you got 4AS then equals 20 minus 5 minus 1.923 minus 1.923 is how many newtons? That equals 6.154 newtons. So the acceleration of the system then is equal to 1.5385 meters per second squared. Okay. Okay, so now I just erased my tension, but tension 1 equals tension 2 equals 20 minus 2AS. So in this case, these tensions equal then 16.923 newtons. And then our other tension, which I'll have to write in black, we'll just call this T3. So T3 then is equal to, well, we have to equal the force on the ramp, at least, so 5 newtons. Plus, we have to fight off this friction, so plus 1.923 newtons, plus the acceleration of the system that's going to cause this 1 kilogram mass to move uphill. So that's 1 kilogram times the acceleration of the system, which is 1.5385. And our tension 3 then is 8.4615 newtons. Okay, so hopefully this helps you with coefficient of friction and ramp problems and Newton's third law.